So now we will just try to explain all these concepts from the perception of Planck's. So Planck's have done some assumption, and on to basis of that assumption, he calculated the mind-blowing. He just do the mind-blowing derivation to explain basically black body radiation. So what is his first assumption? Now, before that assumption, what Rayleigh jeans and Wins have done this particular assumption. The Rayleigh jeans have taken basically the average energy of a electromagnetic wave. He just take that average energy at some particular temperature as kT. So Rayleigh jeans have taken this particular assumption and he just calculated all this thing. And Wins have go with the Maxwell distribution, but he takes that he just go for Maxwell distribution and he just say that average energy is more or less equivalent to h nu e to the power h nu minus h nu by kt. He was just a little bit motivated with basically distribution of Maxwell Boltzmann, and this is also from the distribution of Maxwell Boltzmann, but he just used this energy. He just tried to say that the energy distribution is proportional to exponential function and this kind of situation. Both have works in somehow at some level. Now look at what Planck's have said. Planck's have give the mind-blowing idea. And what he say? He said, no, these all things are different. What he say? He says that energy of electromagnetic wave is equivalent to harmonic oscillator kind of situation, and they are just an oscillatory wave, and every oscillatory wave can be possible energy, and this possible energy can be written as n h nu, where n is equal to 0, 1, 2, 3, and so on. So what are the possible energy? So possible energy means for one possible frequency there is associated one energy. So the energy can be 0, h nu, 2 h nu, 3 h nu. So these are the all possible energies associated to the electromagnetic wave. So it's a mind-blowing idea. And he just take that particular distribution function taken by the Maxwell Boltzmann, and what he tried to do, he just tried to write the distribution formula of energy, and how he will just try to do that, he just say that probability of getting any energy is proportional to e to the power minus e upon kt, and obviously this is given by the Maxwell Boltzmann distribution, and he just try to incorporate all these particular numbers or all this particular energy into this calculation. So what will be the average energy? The average energy is obviously, if we can use this probability formula, then this is summation over EI, probability of getting EI upon probability of getting EI. So this is the fundamental calculation to get the average energy. So what is possible value of EI, or I can say EI, or I can replace it by N. So I can write for the given value of N, because energy is as a function of N. So this will be En, probability of getting En by summation over probability of getting En, and which will be equivalent to, I can write N h nu. This is the one particular mode can have, if N is given, then this is a particular energy, and we have to sum off over N, And what will be probability associated to this? So this is e to the power or exponential minus nh nu upon kt upon summation over exponential minus nh nu upon kt, and n will be started from 0 to up to any level up to infinite. So you can say that all possible energies can be there. This is mind-blowing idea that you can have energy h nu, 2h nu, 3, and energy is discrete. He just incorporated the discrete value of energy into his calculation. This is exactly fundamental thing. So now this is in term of sum. We just try to write all this thing in term of some function. So this is the idea, because obviously in the up to theoretical level it's okay. If we are going to multiply it with the number of modes, then everything is okay. But thing is that our spectrum is continuous, so we have to write this thing in term of some basically continuous, some basically distribution formula, some basically functional formula. So how we are just going to do this thing? So first we will just try to make the thing dimensionless such that we can do this calculation very easy. So what we will do, h nu upon kt I will put alpha. So I am putting h nu upon kt is equal to alpha. So whole calculation can be written as, so kt will be, and this is at the some particular temperature at the equilibrium. So this is at the equilibrium temperature T, and this is in the Kelvin. So obviously h nu upon kt is alpha. So I can put the value of h nu. So this will give us that value of h nu is equal to alpha time kt. So we can put alpha time kt. So in this particular calculation, we have n alpha e to the power minus alpha, sorry, e to the power minus n alpha, and summation over n, and we have summation over e to the power minus n alpha, and we can take kt as our, this will go uh, outside this particular summation term. So this is the typical thing. We can just try to calculate. We will just use a trick. So look at what is the particular trick. So I am just removing all this part. So what is this particular trick behind that? Let's try to use this calculation. So I am just using this calculation, minus alpha d upon d alpha ln summation over exponential minus n alpha. So I can say that this particular thing is equivalent to this. We can check it. We can check it. Don't worry. So what will happen? So minus alpha is there. We have to first differentiate ln. So it will become summation over n exponential minus n alpha. And then we have to go for this particular thing. So next term will be exponential minus alpha, summation term will be there, and we will differentiate with respect to alpha. So that will be minus n. So if we are using all this thing, we can write all this thing as summation over n alpha e to exponential minus n alpha upon summation over exponential minus n alpha. So these and these are the same thing. Kt I can use after that, but I can say that this particular term, I can use this particular term as nothing but minus alpha d upon d alpha ln summation over exponential minus n alpha summation over n. So I can use this all term and we can also multiply by kt also. So kt and these all term are equivalent. So we are using all this term. And now let's try to find what will be this particular term. So if we know, we can say that x to the power n summation over n can be written as 1 minus x to the power minus 1. So this is the typical calculation. You can use this power series. So summation over n is equal to 1 minus x to the power minus 1. What is x here for this particular calculation? X can be written as, so we can remove this summation. So x can be written as exponential minus n alpha. So this is our x. So what we can do, we can just again write all these particular formula in a different way. What we can write kt into minus alpha d upon d alpha, and this whole term ln will be also there. So ln I am using there. This summation term I can replace by a function, and this function is written as 1 minus exponential minus alpha to the power minus 1. So I am using this identity and I am just going to write this thing, and alpha is nothing h nu upon kt. So kt and kt is going to cancel out. So this will be minus h nu. This will be d upon d alpha. And here is ln 1 minus exponential minus alpha to the power minus 1. So finally, we are just going to write. So we have removed the summation and we have written each and everything in term of function. This is the exact idea what we are going to do. We just wanted to remove the summation and we just wanted to write energy distribution in term of some function. So yes, this is a sum function. We can just calculate and finally we can get this particular function. So this will be minus h nu. You can divide, you can just differentiate this particular thing. Then this will be ln will be differentiated 1 minus exponential minus alpha to the power minus 1. Then the whole term is going to differentiate, that is 1 minus exponential minus alpha minus 2, minus 1 will be there, and we have this minus 1 is differentiating, and then we can differentiate this particular term. Is minus is here, so minus is here, and again this minus is here, so this will be only exponential minus alpha. So if we are going to rearrange all this formula, then I can put alpha is equal to h nu upon kt, and this is a very famous formula written as h nu upon exponential h nu upon kt minus 1. So this is a wonderful formula for Planck's radiation, and this is distribution of energy. This is nothing but the distribution of energy. So once we have distribution of energy, and this is nothing but the average energy. So you can just do this calculation. Minus 1 will be cancelled 1, and this will be come downward e to the power minus alpha. You can divide it, you will finally get this thing. So I am leaving up to you. So just you can use this particular formula. So now we can find this. So this is not a minus, okay? This is not a minus thing. So this is the typical formula we are using. This is the average energy. Listen, average energy taken by the reagents was kT, and average energy taken by the winds was something h nu e to the power something. But same kind of thing is here. He just take the average energy using the discreteness energy, and he find the average energy. It's some a distributed formula. And now he have taken the same number of mode. So we are just going to explain what will be the actual radiation formula. The actual radiation formula. So we have average energy here. So what is average energy? The average energy E given by Planck's is all about h nu, and this is exponential h nu upon kt minus 1. And then what will be n nu d nu? And this, he has taken the same formula taken by the Rayleigh, and that will be 8 pi v upon c cube nu square d nu. And finally, we will just try to write the density of energy density. So this will be rho nu d nu is easily written as, you can just multiply this thing by n nu, and this will be distribution of average energy. So E nu, and this can be written as d nu. And once we are writing all this thing, then we have 8 pi h upon c cube, and this will be nu cube. We are using nu cube, and by exponential h nu upon kt minus 1 d nu, and this will be the actual density formula. So this is nothing. So we can easily calculate rho nu is proportional to nu cube upon exponential h nu upon kt minus 1. So this is proportional to this. And when we are just going to plot this, particular thing, rho nu versus nu, then we can find a wonderful plot is there. And this will be rho nu versus nu, and this is my rho nu. I am just taking all this constant term there. And what is rho nu? Is the energy density, or energy density between, or you can find energy per unit volume, energy per unit volume between frequency nu to nu plus d nu. This is the thing. And when we are going to plot it, we can find this will be a wonderful curve exactly matching with the original curve of black body radiation. So this is the curve given by nu cube, or proportionality sum A upon exponential h nu upon kt minus 1. So we can have curve, and we will see up to some expression. And obviously we will see when h nu is very small, it will just give this particular thing. It will be big, then this will give this particular thing. And finally h nu is greater than some particular value, then we can go for the Rayleigh. If we can see it is greater than some particular value, then we can go for Wien's formula. So both are incorporated in the Planck's formula, and this is the actual formula given by the Planck's. And we can just go to understand how this black body radiation can be understood by the explanation of such that electromagnetic wave has not a continuous energy, rather it has discrete energy. And this discreteness will leads to give the explanation of photon. finally by the Einstein in the photoelectric effect. And we can just try to understand what is black body radiation. So in the up next, we will just try to analyze all this thing, and then we will try to do the basic problem, in particular black body radiation. So let's go for basic problem and basic analysis of Planck's radiation formula. So actually the main theory is given by the Planck's, but yes, he used the theory earlier given by the Rayleigh or Wins. He just incorporated all these things and he just tried to give the answer to explaining the black body radiation by discreteness of electromagnetic wave. And he can just easily say that energy is nothing but basically some discrete value of energy is associated to the electromagnetic wave. This is a mind-blowing idea. This is the mind-blowing idea. And finally, this idea leads to go for quantum mechanics. And this, this, this particular energy associated with the frequency can be also explained by Einstein into photoelectric effect, as well as another person, Compton, into Compton effect. That so here he just tried to explain all this thing with the new theory of the theory behind this is, you can say, this is not a classical theory, because classical theory have different approach. It cannot explain black body radiation. So obviously this is the fundamental theory behind this the evolution of quantum mechanics. So let's try to go with some different type of problem. And so this is the all complete theory of black body radiation. So now we are going to solve some basic problem, whatever we have done. So let me recap the first two thing. The first thing today, first we will just go for the problem based on Stephen's law and also the Wien's displacement law. So these are the two formula we have to always keep in mind. So this is the power. The power is given by, for the black body, sigma a t to the power 4. So this is the uh, Stephen's formula, and A is the surface area, sigma is Stephen constant, T is the absolute temperature. But if there is not any black body, then we can use the some uh, extra constant or some extra variable into this particular calculation. So this variable is can be written as P is equal to some epsilon sigma a t to the power 4. This epsilon is known as emittance, or sometime if it is absorbed, then it is also known as absorbivity. And this epsilon is between 0 to 1 for the some real body situation. So it will depends on the body. So for the black body, it is not depend on what is the material, but for the in general realistic sense, we have to include some epsilon, and this epsilon will be given for different body. So this is the thing. And second thing is the very interesting thing, that will be lambda m into t is equal to some constant, and we know this particular constant value. So this particular constant value is approximately 2.9 into 10 to the power minus 3 Kelvin meter. So we will try to solve some problem based on these things. So let's go for the first problem. This is a very interesting but straightforward problem. What we have two black bodies. So we have two black body. Let's say this is some black body A and this is some black body B. So these are two black body, and there are parameters of these two body are given. It is given RA is equal to 4 times RB. So these are the thing, that radius of first body. So RA is nothing but the radius. So this will be radius of A will be 4 times radius of B. Radius of B. So this is the first information we have. that radius of A is 4 times radius of B. The second information what we have, the power of A, will be 10 to the power 4 times power of B. So this power radiated by this black body is related for A and B is something like this. So what we have to do, we have to find lambda A upon lambda B, the ratio between lambda A and lambda B. And what is lambda A, lambda B? Is the wavelength for which intensity is maximum. So means here we have to use the Wien's formula. So how we can approach this problem? This is a straightforward, very simple problem. We have to use this particular formula. So what we have, P is nothing but sigma A T to the power 4, and from the Wien's constant and from the Wien's displacement law, T is proportional to 1 upon lambda. So T is proportional to 1 upon lambda. So what I can say PA upon PB is equal to, sigma will be both for the same black body. So that will be area of A by area of B, and T is proportional to 1 upon lambda. So this will be lambda B upon lambda A to the power 4. And what will be area? So this can be written as P of A by P of B is equal to, area is, this is nothing but the surface area. So this will be proportional to R square. So this will be R of A square by R of B square. And here we have lambda of B upon lambda of A to the power 4. Now we have to calculate lambda A by lambda B. So we can write lambda A by lambda B to the power 4 is equal to RA upon RB square into PB upon PA. So this will be the thing. And now if we are going to write all this particular thing, so this is the thing. So lambda A upon lambda B is equal to, I can say, RA upon RB to the power 1 by 2, because 1 by 4 will get, so this will be 1 by 2, and PB by PA. So this will be PB by PA is all about 1 by 4. So RA upon RB, this is 4 times 400 to the power 1 by 2, and this is all about 10 to the power 4, 10 to the power 4 to the power 1 by 4. And if we are going to calculate it, then we can find this particular value. So we can find the value is all about lambda A upon lambda B is equal to, I think this will be approximately 2. So this will be the answer. So we can find lambda A upon lambda B is equal to 2. So this will be the answer we can get. So this is a very straightforward problem, but we have to always keep in mind what we have to do, where you have to use this formula. So first, it is given for the black body, so we are just going to use this. And second, it is just given that how the wavelength is associated with the temperature, and that wavelength is corresponds to maximum intensity, so we have to use this. So when these two are using in this particular problem, we can easily get lambda A upon lambda B is equal to 2 if I have done all this calculation correctly. So this is the first question of this black body radiation. We have used Stephen's law as well as Wien's displacement law, and we can find the what will be the final answer of this. So let's go for second question. So let's come to next problem. In this next problem, it is given there is a some star and a wavelength associated to maximum intensity is given. So what we have to do, we have to just find the temperature of a star, and we have to also find what will be a intensity of this star, means how much power radiated per unit area. So this is the intensity of this particular star. So these two things we have to calculate. So obviously there is a star and a wavelength. This is wavelength corresponds to maximum intensity, and this is given, as 446 nanometer. So obviously this is nothing but the lambda m. So this will be given as 446 into 10 to the power minus 9 meter. And so first we have to find what will be temperature. So what will be temperature? So for this, what we have to do, we have to just use the Wien's displacement law. Lambda m into T is equal to some constant, and this constant is given by 2.9 into 10 to the power minus 3 Kelvin meter. And now temperature T is equal to 2.9 into 10 to the power minus 3. I can put the value of lambda 446 into 10 to the power 9 meter. This is Kelvin meter. So meter will cancel. This will be into the Kelvin, and we can calculate this particular thing. So this will be 6500 Kelvin. So 6500 Kelvin is a very high temperature, you can assume. So this is the 6500 Kelvin. So this is so strong a concept of getting black body radiation that once we see the spectrum, and once you are seeing the spectrum and you got the maximum wavelength, then you can assume what will be the temperature of that particular star. So this kind of thing is always used into the research associated to stars, galaxies, and all kind of thing in astronomy, and you can say so. But next question is very interesting. What we have to do, we have to find the intensity, power per unit area per unit time. So sorry, power per unit area is basically intensity, energy per unit area per unit time. So this will be basically intensity. So I can find this intensity is nothing but the sigma T to the power 4. This is all about intensity. Once we are talking about power, then we can just multiply with area. But here we need to find the intensity only, and we know the value of sigma. So this is the Stephen's constant. The value of sigma is equal to 5.67 into 10 to the power minus 8, and this is the temperature. We have to take the temperature into Kelvin. So this is very important. So 6500 to the power 4, and now if we can get, this is a 101.2 into 10 to the power 6 watt per meter square. So this is the intensity of that particular star. You can just manage to calculate what will be intensity. So this is one of the fundamental question to understand, to using this particular displacement law, and finally we are using this Stephen's law, and we are getting the answer. So this type of problem will always come into your exam, so there is not any problem. Just try to use the formula again and again. So let's go for next problem. This is very interesting one, and this is really for the practical life problem. So first I will discuss what is this problem, then we will try to calculate it also. And this is a really real life problem. So what is this problem? This is a very interesting. So let me first tell you what is this particular thing, and this is very practical one. So why I have included in this class lecture. So it is given that person skin. Suppose I am a person and my skin have a temperature that is 35 degrees centigrade. We can find it into Kelvin. So no problem. So first question is very straightforward. And what is this? that what is the wavelength radiated with a body of a person which will associated to maximum intensity. So first thing we have to calculate this, and second thing is more interesting, and what is given, that it is also given that environment's temperature is something 20 degrees centigrade, and obviously your body temperature is more than environment. So that is, your body temperature is 35 degrees centigrade, the environment temperature is 20 degrees centigrade, and it is also given the emittance of skin. So skin is not perfectly black body, so it will not 100% absorb or 100% emit. It will keep something inside that, and that emittance that can be measured by emittance, and that will be 0.98. Emittance will be always, or absorbivity or emittance will be always between 0 to 1. And it is also given that typical surface area of particular person is 2 meter square. So it is on an average person typical surface area is 2 meter per square. So what we have to do, we have to estimate loss of power from the body. We have to first estimate loss of power from the body, and second, what we have to do, we have to also find net loss of the energy from the body per unit per day. So net loss, how much energy we are losing per day, we have to that calculate all this kind of thing. So let's try to calculate all this particular thing. So let's go for it. So first question I am just going to calculate. So it is given that theta of skin. Theta of skin, this is the temperature, that is 35 degrees Celsius, and we have to just and we can just find what will be the temperature associated to this particular this will, we can find it into term of Kelvin. So this will be 273 plus 35, so that will be 80 and 308 Kelvin. So this will be temperature, and what we have to do, we have to find that lambda maximum. So lambda maximum into temperature, it's some constant, and once we are calculating all these things, so temperature is all about, we have this particular value 2.9 into 10 to the power minus 3 upon 300 Kelvin, and this will be come out of 9.5 micrometer. So this will be the temperature. So this is in the basically infrared region. So infrared region, so why it is not appeared directly from the sunlight. So but this is the wavelength, this is the maximum wavelength radiated by my body. And this is, sorry, this is not maximum wavelength, this is the wavelength which is associated to the maximum intensity. So this is just using, I am just using this particular thing. And now we have to just see how much energy is associated, how much energy radiated with our body if environment temperature is also given. So what will happen? So first our first what we have, so our body will emit the that particular uh, emit the energy, and it will also absorb the energy. So and this basically that difference between emittance and absorption with the net loss. So this is all about straightforward calculation. So power of emittance is equal to epsilon. So this is epsilon sigma t to the power 4. And if you are, obviously the area is also given, so we have to talk about power. So if we are going to calculate it, that will be 974 watt. So you can just calculate, T is given that 35 degrees centigrade. So here T is basically 308 Kelvin. And similarly, we can calculate power of absorption. So this is emittance. We can find alpha from there. So this will be again sigma epsilon T of this is all about body, and this is all about environment, T to the power 4 into area, and this will be comes to out, and we can find the temperature is 20 degree plus 273, that will be, you can find 293. So from here we can get the value, this will be 155 watt. So we can put it value into there, we can get 155 watt. And finally, what is the net amount of power, that will be, we can get 974 minus, sorry, this will be not 155, this will be actually 819 watt. So this will be 974 minus 819 watt. You can calculate it easily, and this can be come out up to 155 watt. This is 155 watt. So this is the power you can radiate. But now we have to calculate how much energy. So we have to multiply it by the time. So if we are multiplying with time, then power into time is equal to 24 hour into 30 second. So if we are going to calculate all this thing, this is 155 into 24 into 3600, and that Kelvin, you have 3207 kilocalorie. So this much of energy, we are just losing in whole day without doing any work, without doing anything. This much of energy we are going to lose. So this is the one of the fundamental question, the straightforward question, nothing to do with this. First we are using this particular lambda max into T from the Wien's principle, and here we are using the Stefan's principle, and we can that get this particular answer. So this is the one particular problem we can just do to understand which type of situation our body is facing. So even our body is also radiating, but it is not visible because this radiation have wavelength in micrometer, and it is not in the visible range. So why we can have this kind of situation. So let's go for some problem based on basically this basically Planck's and Rayleigh-Jean's formula. So let's try to go for this. So let's come to next problem. That so let's come to next problem. This is a very interesting problem, and it's involved a lot of calculation. But look at this, is the very nice problem. You can see it is given that person have its body temperature at 35 degree. So it has a body temperature of 35 degrees centigrade, and we have to estimate what will be the maximum, what will be the associated wavelength which will give the maximum power or maximum intensity. So first question is this, and second question, it is also given that the environment temperature is 20 degrees centigrade, and it is given that human skin has emittance of 0.98. So it is the some parameter that will tell you about how much energy you can absorb or how much energy you can radiate with respect to black body radiation. So always it will be less than 1. So it is given 0.98. So what we have to do, we have to estimate net loss of power from the human body. And second, we have to also calculate the net loss of energy during one day. So we will estimate what will the energy that we can lose every day. So let's go for step by step. The first is all about that we have to just use the Wien's formula, because it is given that lambda maximum is equal to some constant. Let's say this constant is B upon T, and T is the skin of the body. So this will be skin of the body, and we have to calculate each and everything in term of Kelvin. So this will be 35 plus 273, and that will be 8. 3 plus 7 is 0, so 300 Kelvin. So from here we can get the value, and that will be lambda is equal to 2.9 into 10 to the power minus 3 Kelvin meter upon 308. So lambda maximum. So if we are going to calculate, I think this will be approximately 9.5 micrometer. So this is the first question we are just going to do. The second question is very interesting. So first we have to see how much energy the body emit and how much energy it will absorb. So what formula we are going to do? So the total change in power is equal to just power of in power which will be emitted by the body, power emitted by the body minus power absorbed by the body. So we have to calculate delta P. So first let's try to calculate what will be power emit. So power emit is nothing but the epsilon sigma A T to the power 4, and epsilon is 0.98 into 10 to the power, we can calculate all these things. So 10 to the power, sorry, this is 0.98, and sigma is all about 5.67. So 67 into 10 to the power 8. Area is 2 meter square, and here temperature is 308. So we will just go for 308 to the power 4. When we are going to calculate this thing, I think you will get the number 990 watt. So this is the emitted energy by the body, and then we will just go for that absorbed energy. So absorbed energy is equal to again sigma, and this is the skin body. So this is the skin. So sigma epsilon A T to the power surrounding to the power 4. So this is the temperature you can find from the surrounding. So we can just put again 0.98 into 5.67 into 10 to the power 8. Area is 2. Into this will be 293 to the power 4, because 20 plus 273 is all about 293. And when we are going to calculate it, obviously this will be 803 watt. So what will be change in power? The change in power is 990 minus 803 watt. So this will be approximately, I will get 187 watt. So this is the power the body will radiate. And now we have to calculate what will be the energy. So we are just going to calculate what will be the energy lost during whole day. So we have to use this space. So in whole day we have total time. So time is given 24 into 3600 second. So this will be the time. So in this time the body will radiate this much of energy. So that will be delta P. So this energy delta E is equal to delta P into T, and delta P is 187 into 24 into 3600, and that will come out of a very large number. You can see this will be 16156800 joule, and we can convert it into calorie. So then this number is 3861 kilocalorie. So this is the number you can just calculate, and you can see this much of energy we are losing every day. We are losing every day uh, without doing any work and anything. So this much, naturally, this much of energy we are losing. So at least we need some food to overcome this much of energy. So that is different issue. But yes, our body is also radiating the wavelength, but that wavelength is not visible because they are in the range of some micrometer. So I have calculated that is their range of some 9.5 micrometer, and you can see that this type of problem we can also try to understand what is going to happen our body, and how this spectrum can tell about the temperature, and how this temperature is related to all about radiating the thing. And we can also calculate how much energy we can radiate, how much energy we are wasting every day due to just only due to this radiation. So this is the wonderful problem to using a Stephen's law, and particularly wind displacement law. I hope you can just recheck this calculation. I am sure this calculation have done correctly by me, but you can recheck all these things. So next part of questions, we will just go to do little bit of question on mainly this uh, Planck's formula, and we will see how we can analyze all kind of things. So let's go for next level of problem. So let's try to do some problem basically on Planck's distribution law, and mainly we have done on the calculation based on Rayleigh jeans and all this kind of thing. So let's try to go for it. So first question is very interesting. So what we have to do, we have to find that number of modes between wavelength, that is 4990 angstrom, to 5010 angstrom into 3 dimension. So angstrom in 3 dimension. So we have to just calculate number of mode or number of possible waves between these range of wavelength. So we know that number density is given by, so this is n nu d nu is given by 8 pi nu square upon c cube d nu. This thing for the 3 dimension case, we can easily write this particular thing. And we also know that c nu is nothing but c upon lambda, and this is that only difference. So we can take the mod value. So d nu is equal to c upon lambda d lambda. I can just take the mod value. So negative sign will incorporate it into this. So once we can get this particular value, that is all about n lambda d lambda, and this value will come out. So this is 8 pi upon c cube. Nu square can be written as c upon lambda square, and d nu can be written as c upon, this is c upon lambda square. So c upon lambda square d lambda, and which will equal to, that is all about 8 pi upon lambda 4 d lambda. So this is the particular number between lambda to lambda plus d lambda. So now we can calculate the value of d lambda. The d lambda is nothing but 5010 minus 4990. That will be 20 angstrom. So negative sign is had not any relevance into this particular thing. And now we have to also calculate the average value of lambda into this. So average value of lambda, we can write 4990. So that is the average value of lambda plus 5010 by 2, and this thing is approximately 5000 angstrom. So this is the particular thing, and now we can put it all this thing into this equation, and what we will get, we will get 8 pi upon 5000 angstrom means 10 to the power minus 10 meter. 4 will be there, and this is 20 into 10 to the power minus 10, and we will, when we are going to calculate it, then this value is approximately 8 into 10 to the power 17 per meter square, that is number per meter square. So this much of number, so look at 10 to the power 17 number of waves can be possible when your lambda is approximately 20 angstrom. So lambda is 20 angstrom. So then you can find approximately 10 to the power 17 per meter is the particular value. So this is the one of the wonderful problem. So you have to always keep in mind that which formula you are going to do. This is for the 3 dimension. Sometimes same problem can become for the 2 dimension. Sometimes same problem can be for the 1 dimension. So you have to just calculate this thing particularly, and then you can go for accordingly 1 dimension, 2 dimension, and use this same concept. So let's come to next problem. This is again very wonderful problem. So what we have to do in this problem basically, so in this problem what we have to do, we have to just find the just to approximate our Planck's constant for 2 different cases. The first cases is all about h nu is greater than kt, and second cases is all about h nu is less than kt. Means we just want to understand what will happen to Planck's constant when frequency is small, and what will happen to, sorry, not Planck constant, that Planck distribution when frequency is small, and what will happen to Planck distribution when frequency is big. And obviously the reference is all about kt. Kt is also the energy, particular the dimension of energy. So with the reference of kt, if h nu is bigger or h nu is smaller, let's see what is going to happen, and you will be surprised that will be exactly match with Rayleigh-Jeans formula as well as the Wiens distribution formula. So let's try to do this particular problem. So what we have that energy density formula, h nu, sorry, rho nu d nu, is this is not but energy density, and this will be 8 pi upon c cube nu square, and h nu, and this will be h nu upon kt minus 1 d nu. So this we have derived. What we have to do, we have to first calculate if h nu is less than kt, means frequency is very small, and then we have to approximate it what will happen when h nu is greater than kt. Kt is nothing but the energy at equilibrium temperature T. So this is the energy of equilibrium temperature. So let's try to go for this. So what will happen for the first case? So first case, if h nu is less than kt, then this number is very small. And what we can do, we can just write rho nu d nu is equal to 8 pi upon c cube nu square, and this h nu will remain there. What we can do, we can take the Taylor expansion of this exponential term, and we will just take the first order term. So this will be 1 plus h nu upon kt, and the higher order term we are neglecting, minus 1 is there. So this will be cancel out, and this is also cancel out. So this is exactly what we have, 8 pi upon c cube nu square kt, and this is all about rho nu d nu. So this is all exactly we have found for the Rayleigh-Jeans formula. Exactly same thing we have get from this particular Rayleigh-Jeans formula. Let's go to the second one. The second one is also very interesting. For second one, what we have h nu is greater than kt. So if you have h nu is greater than kt, then we can write rho nu d nu is equal to 8 pi upon c cube, and this is nu square, and h nu, this is h nu upon kt minus 1. So if h nu is greater than kt, this number is very large. So this number is very large. We can neglect 1 with respect to this number. So this number is very large. So E h nu upon kt is very, very greater than 1. So we can approximate this formula as something that will be 8 pi upon c cube, and this will be nu square, and it can written at h nu into e to the power minus h nu upon kt. I can neglect this particular thing, so this will just go above, and we have discussed that this is approximately same thing as the Wien's formula, Wien's distribution. So this is greater for nu is, so this is approximated value for Planck's when nu is greater than, very, very greater or in comparison to kt. So whatever is the greater or a smaller, we have to some reference. And what is reference? The reference is all about equilibrium temperature. So when you are saying that nu is bigger with reference to the energy associated with the thermal energy, that is kt. So when h nu is greater than kt, then you have this particular thing, and when h nu is less than kt, for the smaller thing, you have this particular thing. So this is the exactly approximated value. So from the Planck's value, we can reach up to Rayleigh-Jeans, we can reach up to Wien's particular formula. So this is one of the wonderful problem we can ask they can ask into examination, what will be the approximated value for this. So let's go for next problem. So let's go for next problem, and what we just want to know that intensity. So we have to derive from the Planck constant. So sorry, Planck distribution. From Planck distribution, we have to prove that intensity is proportional to T to the power 4. So obviously we can prove this thing by, so this is the thing we have to prove, that intensity is proportional to T to the power 4. So before going to this proof, let's try to understand some basic thing. So suppose we have this kind of situation. Or you can just, this is just a straight line. So this is the area A. This is the area A. And if the radiation is coming in a unidirectional, so they are just coming perpendicular to this particular plane, then what we can get? We can get intensity is nothing but equal to C into rho. What is that concept? The intensity is nothing but energy per unit time per unit area. So this is the whole thing. So what is this particular? C is the speed of light, and this will be that energy per unit volume. And if we can write, this will be cross section area into this length. This is the length. And if so we can assume that this length is nothing but the speed of light is moving in time in 1 second. In 1 second. So why we are multiplying with C, then we can get intensity is nothing but C into rho. But this formula will be correct when the radiation is just perpendicular to this particular cross section area. But in general, what will happen? In general, the radiation is not coming perpendicular. They are coming in the oblique axis, all possible axis, all possible direction. So this intensity is effectively less than zero. So what is the effective intensity for this particular? You can just see when this is coming in an oblique direction. Suppose this is the area. So this is the area I am talking about. And if the radiation is coming all possible direction, then obviously this intensity we can calculate. This will be C rho by 4. So this will be due to that effect of solid angle. We can find this will be C rho by A. They are just coming with some angle with the normal. So this will be C rho by A. The effective intensity is 4 times when it is coming just in a normal direction of the area. So now this rho is density for all possible frequency. So what we can do, we can write this intensity formula as C by 4 integration of, and this will be 8 pi nu square upon C cube, and this is h nu upon e to the power h nu upon kt minus 1 d nu. So we are integrating the density. We have density formula. We have earlier density formula from Planck's, that is rho nu d nu is equal to, we have 8 pi nu square upon c cube, and this is h nu e to the power h nu upon kt minus 1. So we, and d nu is also there. So if we are going to integrate all our possible thing, then we can get the total density rho. So now before integrating, so we can take all the term outside. So that will be 2 pi, and this will be c square, h is there, and inside we have nu cube d nu and e to the power h nu upon kt minus 1, and we are talking about all possible frequency, whatever with the possible frequency between 0 to infinity. So we are talking about all possible frequency. What we are doing, we can just parameterize this integral. So what we are going to do, h nu upon kt is equal to, let's say, x, then d nu is equal to kt upon h dx, and when we are putting it here, then we have 2 pi h upon c square, and this term we can, nu is can be written as kt upon h to the power 4. 3 is here and d nu for 1 is d nu, so this will be to the power 4, and inside this integration we have x cube dx e to the power x minus 1, 0 to infinity. And now from here we can easily find, this is an integration, this is nothing but just a number. So we can find I is proportional to, so from here we can find I is proportional to t to the power 4. But if we are going to do this integration is well known integration. We can find with a different way, but currently I can just writing this equation, that is kt upon h to the power whole 4, and this will be pi 4 upon 15. So when we are going to calculate all this thing, then this value is equal to 2 pi to the power 5 k to the power 4, and this is c cube, and that value is h, sorry, this is c square, not c cube, this is c square, and this is h cube and t to the power 4, and this is exactly matching with the uh, Stephen's law. This is exactly matching, that is nothing but sigma t to the power 4. This is exactly matching with the Stephen's law. So you can derive this Stephen's law also from the Planck's law. So this is one of the wonderful thing. The main thing is you can just do this integration, that will be pi 4 by 15, but don't worry, this you can prove that intensity is proportional to T to the power 4. Once you can prove that intensity is proportional to T to the power 4, then power is also proportional to T to the power 4. So this is the wonderful problem. We can use all this integration and all kind of thing, and we have get all this particular Stephen's law from the Planck's radiation law. So this is the Planck distribution, and we can, or this is energy distribution from the Planck's, and we have just find what will be the Stephen's law. So the value of sigma, I can write this value of sigma is all about. So if we want, we can write we have getting the value of sigma. The value of sigma is all about 2 pi to the power 5 k4 upon c square h cube, and this value we can find 5.67 into 10 to the power minus 8 watt per meter square Kelvin 4. So this will be the value of sigma you can calculate. So, and the trick is what? You can make it dimensionless. This is the actual trick. Once you can make it dimensionless, you can find each and everything very easily. So this is the one of the wonderful problem you can solve for basically from Planck's to Stephen's law. You can just go for this. So let's try to derive the Wien's displacement law from the Planck's radiation law. So let's try to go for it. So first, what we have to do, we have to just write that Planck's radiation law in term of wavelength. Then we can go for this particular thing. What is Wien's displacement law? That intensity will be maximum at some particular wavelength. So we have to calculate that particular wavelength. So let's see what is idea behind that. So we have this particular the distribution formula, rho nu d nu is equal to, we have 8 pi nu square upon c cube, and that will be h nu upon e to the power h nu upon kt minus 1 d nu. Again we are using the formula nu is equal to c upon lambda, and d nu is equal to all c upon lambda square d lambda. And when we are putting all this thing into here, nu is equal to c upon lambda, d nu is equal to c upon lambda square, h nu upon h nu is equal to hc upon lambda, then we can get this particular thing d lambda d lambda. So rho lambda d lambda is equal to, that will be 8 pi hc upon lambda to the power 5, and this is e to the power hc upon lambda kt minus 1 d lambda. So we have to just for the maximum intensity, means energy density will be maximum, we are keeping that area and all other thing constant. So d rho upon d lambda must be equal to 0, and which means we are have to just calculate the value d. So this will actually 8 pi hc we can take common. So we have to just differentiate that d upon d lambda, lambda to the power minus 5 into e to the power hc upon lambda kt minus 1 to the power minus 1. So we have to differentiate them, and when we are going to differentiate, and this must be equal to 0. So when we are going to differentiating all this thing, I can take 8 pi hc as common, and inside bracket we have minus 5 lambda to the power minus 6. We have differentiate this thing. We are keeping this thing as constant. This will be e hc upon lambda kt minus 1 constant. And second term, when we are going to differentiate, this will be lambda to the power minus 5. This will remain same. We are differentiating the whole term, e to the power hc upon lambda kt minus 1. This will be minus 2, then exponential. This will be hc upon lambda kt and then lambda. Then we have hc upon lambda square with minus sign. So this must be equal to 0. What you can do, you can take something as a common. So we can, and this has not relevance because right hand side we have 0. So what we are taking common, we are taking lambda to the power minus 6 and e to the power hc upon lambda kt minus 1. Minus 1 will be common, and inside the bracket we have minus 5 plus hc upon lambda kt, and we have e to the power hc upon lambda kt by, and this is minus 1 will come here, so this will be e to the power hc upon lambda kt minus 1. So this thing is there. So this particular thing cannot be equal to 0. It is not going to 0. So what will happen? This term is only going to 0. So only this term is only going to 0. So what will happen? We can find this minus 5 plus hc upon lambda kt, and this will be, I can divide e to the power hc upon lambda kt on numerator as well as denominator. So then we can find 1 upon 1 minus e to the power minus hc upon lambda kt must be equal to 0. So from this, so we have to just solve this particular equation. But solving this particular equation is a very tedious task actually. So you cannot solve it directly, but you can solve with the help of computers or numerical problem. So you can, but what you have to solve actually, you have to solve a very interesting thing. I can use the different color. So that will be, we have to solve 5 lambda kt upon hc must be equal to 1 upon 1 minus e to the power minus hc upon lambda kt. So we have to solve it, but you cannot solve it directly. So you can solve it only by the numerical method, because it is very difficult to that find the lambda directly from here. But once you will able to solve from the numerical method or the computer programming, you can easily find the value of lambda is equal to hc upon 4.9 kbt, and this value is actually 2.9 into 10 to the power minus 3 upon T, and this will be meter Kelvin. So this is corresponds to maximum intensity. Lambda m is corresponds to maximum intensity. This corresponds to maximum intensity actually. Intensity. So what we have one particular expression that is very nicely known as Wien's displacement form, and Wien's displacement will tell you that lambda m, and this is lambda corresponds to maximum intensity into T is equal to all about 2.9 into 10 to the power minus 3 meter Kelvin. So we can find each and everything from Planck's distribution law. Each and everything. So why the Planck distribution law is a complete theory for the black body radiation, and you can think that we can go to Stephen's law, we can go to Planck's distribution law. Sorry, we can go to Wien's distribution law. We can go to from here Rayleigh Jeans. We can go to Planck Wien's distribution, Wien's displacement law, everything, whatever we have observed from the black body, we can easily use for, we can easily uh, discuss it, or we can easily justify it with the Planck's radiation law. So this is all about the basic case of your basic analysis of black body radiation and related all different types of problems. Okay, thank you.